Welcome, everybody. So today's presentation is about exploring compute usage from user-facing portals, like the title suggests. This is actually picking up directly from previous presentations that we've done on this topic. Specifically, most of them have been ways of understanding what we call expected wait times in the queue by building up tools to visualize the usage that researchers do on the compute clusters through the scheduling software. In those presentations in the past, we've described tools that we've been developing, either Python packages or procedures that we run on the clusters themselves. But what's been happening, especially over the past year, is in the data analytics team, we've been working closely with the scheduler national team in building data structures that feed portals that staff have been using for various reasons whenever we're supporting researchers to assess how jobs are getting deployed to the system and helping researchers reduce wait times and also get the most out of resource allocations. Aspects of those portals that staff have been using for various reasons are now being made user-facing. This is pretty hot off the press, like they've sort of been coming available. They aren't documented yet, but I want to basically do the translation of presentations I've done in the past and how researchers can now do that by visiting portals to view some of the analyses that we've talked about in the past. So as a bit of an overview, I'll talk briefly about the previous presentations, specifically two of them. One of them where we described a Python package called viewclust that's available at GitHub and was sort of spearheaded by my colleague Tyler Collins and used data structures that were developed and maintained by a team under the direction of Mark Hahn. That presentation really described how to calculate the usage time series and examine the amount of queued resources relative to the used resources relative to an account's target share to estimate when there would be long wait times and how to minimize that. The second presentation is one, so the first presentation always leads to the discussion, and whenever we're dealing with wait time tickets, the discussion of, well, how do we actually know what to request whenever we're submitting jobs? How do we really get a good picture of the resources that are actually required to run the process that you're submitting a job for? And I did a presentation where we would start an interactive job and then start a second terminal and then examine the resources while we change properties of an array that's being built in MATLAB or something, and then just watch the resources that are available there, and then using that instance of top on the node to build assessments. I'm going to redo that today, but then look at the properties as a time series in a portal for the Narwhal cluster in this presentation. So the prerequisites to this are really understanding what job shape is and the measurement of resource consumptions. So this is an introduction that I give on all of these talks, just to understand what it is that we're doing. And this is really sort of a prerequisite for understanding how the compute clusters are managing the fair allocation of resources across, all researchers that are submitting whatever they want to the system. Then there's the job resources allocated pending and the target share of the account. So measuring how much an account has pending versus running in relation to what the expected share or the expected amount of usage that an account can expect is really the main thing that we look at first whenever there's an issue with wait times. After that, I'll show examples of examining those measurements at a user-facing portal. That portal is called portal.alliancecan.ca. This portal is being spearheaded by one of my colleagues in the East Coast at AceNet, Sergey Khan, who is building this Dash portal and building the data structures that underlie the measurement of resource. I'll call it consumption, but that. Now, after that happens, those measurements and what the scheduler actually sees is the resources that are dedicated or reserved to a job. Now, if you want to, a big priority is to minimize how many resources you're reserving for a job in order for it to be able to fit more easily onto the resources that are available to the scheduler. But to do that, you need to understand what's actually being used within what's being allocated to the job. So we talk a bit about allocated versus used job shape. And then finally, we'll talk about the second portal, and that's exploring the job resource usage at the portail at narval.quebec.ca. So these other portals, for example, for the Narval cluster here, are being developed by another colleague of mine called Simon Guibault, who's a system administrator in Calgary, Quebec. The tools that he's developing are basically allowing analysts and now users to have a view into what's typically largely only available to the system administrators that have root that can watch the actual procedures, which is a level down from what the scheduler sees and what all users can basically just query on the system. And what he's done from that basically feed of information coming from those lower levels is he's built portals that give a view that's sort of a step below what's available in basically the scheduling view portal developed by Sergey Khan. Okay, so let's see what we got here next. Right, so the first presentation that's in the past, if you go to our YouTube channel, there's basically an episode like this of our user seminars called Visualizing Job Properties for Wait Time Assessment. And what this presentation does is it basically reviews this ViewClust Python package that was spearheaded by Tyler Collins. And in that seminar, we demonstrate using that Python package to build these figures inside of a notebook. So there's instructions on how to clone this onto a system. It queries job records, and then it builds all of these measurements, and then you can get an idea of exactly how that's done. But you can also visualize important parts of the usage and the queued resources that are running. So what we're doing in this presentation is we're showing how figures like this can now just be viewed by users in a portal. Then the next presentation that we're working from is a recording which was part of a 2-Minute Tuesday series, so a very short recording called Estimating the Memory Footprint of Your Code. Now, we talked about the memory footprint, but you can also actually check how much resources are being consumed across other domains of the resources. And this example starts an interactive job so it starts an interactive job in one of these terminals here. And then once that terminal begins, it opens up Octave and it starts building arrays of different sizes. And then in a second terminal, it's actually SSH'd into this compute node, and then it's just monitoring top. And in particular, this one was monitoring the memory size as the resources changed as we assign different sizes to a random array in MATLAB. Now, what I'll do at the end of the presentation today is give this demonstration exactly the same way, where I create an interactive job. I sign into that node in another terminal, and then I monitor the resources. I start up MATLAB or something, and I start assigning different sized arrays, and then I watch it in the second one. But after that, what we'll show is you can actually go to this other portal for the Narval cluster, and then you can find that job, which is an interactive job, and then you can actually look at the resources that it consumed as a time series. And this is really the gold of being able to do true resource estimation for submitting ideal parameters in the jobs. And if you can submit ideal parameters in your jobs, you will get ideal throughput. You'll be maximizing how much of the system you can use. Okay, so that's basically the starting point. If you want to go over those seminars, they're there and you can still use those tools. But what we're focusing on today is how to basically do everything that's talked about in those, or the important parts of it, and more, but just through signing into a portal. So what we're talking about here is basically a visualization of how we measure the number of resources that are consumed. So jobs can be visualized as multi-dimensional rectangles. In this case, we're talking about basically a number of resources over time, and then an amount of resources. So each one of these multicolored rectangles is a single job. Okay, so this gray and green rectangle here is a job where it has a submit time, it has a start time. The green section is the duration that it ran, and then this other line here is the time limit that was requested for the job. So all of these properties can be sort of viewed in what we call a job stack. So each one of these records is a single job. The green time is the duration that it ran. And then the gray time over here is the duration that it waited. Now, importantly, the height of each of these jobs is the number of resources that it consumed. So what we call that in the scheduler, and the way that this height measurement is used by the scheduler is referred to as billing. Now, of course, we don't charge anything for usage of these systems, but we bill the reservation of resources to the fair share of the account. So the height of this job is the amount of resources that is basically tallied against an account's fair share of resources. So the way that we visualize the usage of all of the accounts on the system, and this is something that we monitor as staff to try and determine if there are accounts that are experiencing unexpected wait times or are struggling to meet their target share. So what we do in the next slide is by summing the billing units at each time point across all the jobs, we can provide a series of resource consumption. So what we're looking at the bottom is really the key of understanding when there might be wait times and understanding if there's anything that a research group should focus on reducing the billing of a particular workload. So in this case, these are figures that are generated from that ViewClust package that we demonstrated. So across all of these jobs at this time, if we sum all of the green, we basically get this spike of usage. Now, importantly, this is the usage for an account. For example, your default account on the system that you submit jobs to, or your rack account that your team is submitting jobs to. Each of the different colors represents a different user within the group that was submitting jobs to that account. Now, what we can see is, of course, that the resources that are consumed goes up and down and is often idle, where researchers don't need to be submitting jobs at that time. It stays. Now, the scheduler and the fair share works entirely by what's called the fair share. And all accounts have what's called a target share. So there's a gray area down below. That line corresponds to this account's target share. What the target share means is that this account can run substantially more resources than their target share at any particular time. This is called a burst. And at other times, they can run substantially less, but that's totally fine. It's expected. The important property is that regardless of how many resources are being submitted to the queue, the scheduler is going to try and maintain that over time, the average usage is basically the target share. So there's one other thing, you can barely see it here, but there's a gray line right here that peaks there, and then drops down. That gray line is the number of resources that are pending at each time. And we calculate that by summing the amount of gray area at any time. So all of this gray here is a bunch of resources that are waiting in the queue. And here, we can see there's a whole bunch of pending resources, way more than the allocation, but nothing is running at that time. And this is where researchers expectedly and understandably get concerned about the ability for them to reach their target share. So the next view, which is basically what we use to determine a expected or an unexpected wait time, is if we calculate the cumulative sum and then we display it. So this is the figure that we were looking at before. We have the target share and then we have the actual usage. If we compute the cumulative sum of the target share, we get this straight diagonal. And then if we compute the cumulative sum of the usage, we can see that it goes over the target, then it starts oscillating, and it's kind of keeping around it. That's why the scheduler was delaying these jobs, because at that time, the usage cumulatively was above the target share, and it needed to get back down before it could submit more. And this is the sort of oscillation that we would expect to see in the cumulative sum, as the scheduler is trying to maintain that target throughput. Now you can also see, because this account was idle for a while, the scheduler actually allowed it to catch up to its cumulative target share. This is something we want it to be able to do, but can only do it to a certain extent. So this is a great example of the sort of view that we use whenever there are concerns about wait times, and there are definitely a lot of concerns about wait time in this environment, because there are so many researchers submitting so many jobs, and we have to try and maintain the best outcome for all researchers. And a lot of researchers only submit jobs infrequently, but they need to sort of accumulate all of that throughput during those times. So we're constantly monitoring. This visualization is developed by the Data Analytics National Team, but we provide reports of these to the Scheduler National Team to make sure that the way that they're configuring the scheduler is allowing all of these things to happen. So this presentation now is about making these visualizations available to researchers, so that the things that staff check, typically whenever these tickets come in, users can start checking those right away and monitoring this and have an understanding of it before having to submit a ticket. So let's see what the next one is. Okay, so here we go. This is a view of the portal .alliancecan.ca. So I'll just go over a few things, but this is a this is a view that is the same as what we were looking at from the ViewClust Python package, except whenever you go to the site, this just ends up being displayed for you. So I took this screenshot logged in as staff, and whenever I do, there's a user form here. Whenever users are logged in, that's not there. It just assumes that whoever you sign in as is the user. Whereas staff, what we can do is we can go look at other at research groups and users to get the same view that you have. Then all of the accounts that a researcher belongs to, so each researcher, each student or staff or collaborator can be part of various projects as different roles within the system. Once you sign in as a specific user, this will list all of the accounts that you can see, and then you can pick it. So whenever you're a part of a resource allocation project, you can select that one, and then it will display this line here is basically a sample of all of the account information once a day, and the red dots correspond to that account's target share of the system on each day. Okay. And then what we have is the bar graphs of the instantaneous usage over time, broken down by the users that submitted the jobs that are in there. And then, of course, you have here, this is looking at the Narval system, and it's presenting a specific time interval. Down here, I've basically just edited this out because I'm looking at a specific research group, so I've just removed the information. But whenever you pick an account, it gives the information about that account. And then down here you have parameters. So CPU equivalent is the measure that we're looking at, and CPU equivalent is basically the billing measurement that's used on the clusters. So the next thing that's important, so we looked at that, and then what usually happens is the concerns come in situations like this. So what I've done here is in the legend, initially when you sign in, this gray thing, the queued jobs or the queued resources, is not selected. But if you click on that, it will then show the gray bars. So these gray bars here, and then these gray bars here correspond to the number of resources that are pending in the queue. That's the sum of all of the resources for jobs that are currently waiting in the queue at that day. So this plot shows daily resources. So that's viewable just by clicking this. This is the first thing that we do whenever there's concerns about wait times. We check for what that is. And initially this is a concern because there's resources waiting in queue even beyond the target share, but at that time there's nothing running. So there's a delay there. So what we do from here is we try and figure out why that's happening. Let's fumble around here a bit. Okay, so during that same interval, what we can do, and this really gives you the view that we're concerned about, is we can change the summation to, instead of the total on every day, convert it to a running total. So now we see the diagonal line, the cumulative sum of the target share, and then we see that the usage is not keeping up with that target share, even though we know at this time from the last one, there were jobs submitted, but they weren't running. Now, the important thing to recognize here is that somewhere in all of this, the scheduler is making the determinations about when this account's jobs have the right priority, and then using that to determine if this account's jobs are at a higher priority than others that are competing for the same resources. So the thing about it is with this view at this time, we know nothing about the past that might be leading to this being an expected period of wait time. So I think on the next figure, I just, right. So what I've done here is I've just extended the time. So this one starts at June 16th. And then if I look at this one, so June 16th is right here. And what I've done is I've just extended this back a month. So it's in May. Now, what we see in May is there was actually a huge burst of usage where it went from almost nothing to pretty much double the target share trajectory. And then the window of concern started right here, where cumulatively that account, in terms of how the scheduler is perceiving this, is still way above target. So in this case, what we would say is, yeah, like this is an expected wait time because this account cumulatively over the period of time that the scheduler is still interpreting this account relative to other accounts in terms of all of them trying to reach their target, this account is still above its target share, and the priority of jobs submitted to this account are going to be lower because of that. So by extending the time window to see what happened in the past that the scheduler is configuring, which is typically about a month, we can see why those wait times were happening. And then what we can do from there is try to interpret if this very large amount of usage that happened right here is something that could be reduced in the future, or if there was some reason why the sort of the time series of the usage ended up resulting in unexpected wait times. So what's next? I think next we convert this back to, instead of the cumulative usage, we convert it back to the basically just the total, the daily total of resources. And importantly, you see that this is a huge burst of activity, and the color represents that these are two different users. So in this case, you'll have one user that had this wait time here, and then it waited and waited and waited, started running, and then they experienced a bunch of more wait times here. But as far as this orange user is concerned, they were not expecting any wait times here. But this other user somehow managed to use a huge amount of resources. And then what we want to do from here is figure out how this project can coordinate the resource usage. And in many cases, if the job size is very different for the different users, a single user can overwhelm the account and pretty much lock out other users because their jobs are just easier to run. And this is something that we work on with researchers a lot. Okay, so I think that's really the view that's available to researchers at this portal, and this is the portal at alliancecan.ca. And these are basically the units that we use for reporting resources. The database that underlies this, we use for various reports where we're monitoring and generating alerts of accounts that seem to be in a state where they're likely experiencing pain in the queue wait and might end up having difficulty achieving their total resource allocation. And it's, of course, it's great, intuitive. You have like a long history of usage in the past. And if there are wait time tickets, this is what I always look for. I try and deal with as many of the wait time tickets as possible, and this is where I go first, and then I'll start sharing the views with the researcher in the ticket. Now, the conversation, whenever we start trying to assess how to get rid of these wait times, is often about how the job shape, so how many resources are requested for how long. The conversation always turns to whether different types of resources could be requested, or processes in the actual task the job is running can be reduced so that the job shape can fit better into the compute resources available in the competition with all of the other jobs that are in there. And this is like another talk, but the shape of a job has a very large impact on the job's wait time. And there are other counterintuitive things like the users within an account, the relative usage of each of those users has no impact on the job priority. So one researcher who has used twice the amount of allocation for a week, if they submit a job the week later, and then another user in that account that has never used the account submits a job, there's no difference in the initial priority of those two jobs. So it's the priority is only dealt with the account, not the users within the account. That's a very counterintuitive thing, but is important in terms of all of the accounts being able to reach their target share. The other thing is that wait time in the queue has pretty much zero impact on the priority of a job. So if there's a job for an account that's waiting in the queue, the duration that it's in the queue doesn't change its priority. The only thing that's changing its priority is really the priority level of the account. So if other users are able to get jobs running, that will keep the account's priority low. And then this one job that's having a hard time to start just sits there indefinitely. And what we do is we really try and make sure that we understand when that's happening and find other ways of submitting those jobs so that it works. So the important thing that we want to get to here is, how do you tell what you actually need? Whenever you're submitting a job, how do you know what the parameters are that you actually want? And this can be a pretty difficult thing to determine because there isn't a really clear view, but this other portal is really a view into that aspect of it. So we talked about this job shape thing a little bit in terms of how we measure usage over time. So let's just look at this job right here. So this job had a submit time here and then a start time here. The job ended running here, but the distance from here to here was the time limit that was submitted to the job. So right away, we know that this job could have been submitted with like less than half of the actual time that was requested. So this duration, if you submit a shorter runtime, depending on the interval, first of all, you can get access to more and more resources. More nodes are available to run shorter jobs. But also, if it's a shorter runtime, it can fit into gaps that are on the system where there are high priority jobs that are going to start in a little while, but there's still like a bit of time left before that's going to start. So other jobs can get fit in at a lower priority. What we don't see here is, like, let's say the height of this is based on the amount of memory that it requested. Let's say this is like a measurement of 100 gigs. What we don't see here is that potentially the job only used 20 gigs. In that case, if this job had requested only the 20 gigs, not only would it have been able to fit into smaller memory gaps on the cluster, but it would only be billed a fifth of the resources towards the account's fair share. So understanding the memory consumption of a process is very important. And we note here that what's billed towards fair share is what was reserved for the job. So what the job requested, not how much it actually used. So you're kind of this issue of understanding the actual memory requirements of a job has double impact. You get billed for it, whatever you asked for, towards your fair share, which will reduce the priority more than necessary for all subsequent jobs. But also, memory, it can be a very difficult thing to fit into the compute nodes. And if you're requesting too much memory, it's going to fit in fewer spots and have to wait longer for enough priority to build up in order for it to fit in there. So the next part of this presentation is really about seeing that line. How much memory is actually being consumed in the jobs that we're running? So let's see. So here's a view of basically that same account, but now we're at the Narval portal. So the Narval portal has a bunch of different things, and these portals are specific to clusters. Right now, the full package is really only available in the Quebec clusters where Simon Guibault is staff, and he's really pioneering all of these things, not only building the data structures and the data feeds available, but building the portals to view it. So this one, I think we're looking at what's called a user summary here. And I think this is pretty much where you end up going. So this is the actual same time series that we were looking at of the consumed resources. So this is basically what the account was being billed. Now, one thing that isn't available yet in the dash view, but is coming, this red line corresponds to the account's priority. So if you're looking in the schedule, it would basically be what's called the level FS. This value, so if it's at 1, this line that I'm drawing right now is basically the at target line. If the red line is above that horizontal line, it means that the account, the jobs for that account are going to have a high priority. If it's below the red line, the jobs for that account are going to have low priority. So I think the issue that we were looking at before happened right here, where one account had submitted a whole bunch of jobs during this gap, but they weren't starting right away, even though they didn't have anything. And the thing is, that great big burst of usage that happened here tanked the account's priority. And then there continued to be usage, and then it didn't recover until over here, whenever that user started running jobs again. So this red line directly relates to the priority of that account. Whenever it's low, it's going to be more difficult for that job to compete for resources in the scheduler. So this is exactly the thing that we're looking for whenever we're trying to understand if a account is experiencing expected or unexpected wait times. There definitely are unexpected wait times where a job shape is just completely underserved by the configuration of the system. And that's something that we work hard to address when we find instances of those. So that's the top view, which basically adds the explicit representation of what the account's target share is. But the green line is basically what we were looking at before. Down below, it actually in the previous view, and this is a representation of the users as well. So now this is the usage, but it's colored by which user was using the resources. And then we can see again here that this big burst was one user, and then the user that suffered later was actually a different user, where that feels like a very unexpected wait time for that user. Okay, and then from there, we start to get different breakdowns. So here we now see things like the same usage time series. This is the allocated CPUs, and that's what we've been looking at so far. This is basically the sum of what was allocated to the resources. And then here we see this is what was actually used. So a view that we don't have from the scheduler is what actually was being consumed inside of those resources. And here we see that there was the allocated resources, what was asked for and reserved for the job, but now we see the same time series with what was actually used within it. And these two figures are pretty much exactly what we want to see. These two things look pretty much identical. That means that this group has been doing a great job at understanding how many resources they actually need to run in terms of the number of CPUs that are required. And then we can see here is actually the timeline of the wasted CPUs. And this scale is nothing. It says 100 cores, whereas up here, this is in the 10K cores. So this looks great. If there was an issue of requesting more resources than necessary, it's not in terms of the number of cores being assigned to the job. The next page, and whenever you're at this site, this is really just a matter of scrolling down in the view. The next one is the allocated memory. So the allocated memory in this case is pretty giant, like 40,000 gigs, but the used memory is only 5,000. So there is a substantial amount of waste, and this is actually the case for both of the workloads that were happening. Now, this looks kind of shocking, but this happens very frequently for very good reasons. For example, a lot of the workloads, particularly with groups that are doing multi-core jobs, are requesting entire nodes to work at once. Whenever you request an entire node, you need 32 cores, but you might not need all of the memory on the node. In fact, you might need a very small amount of memory, but you need the entire node. So in this case, that's what's happening. In fact, I think the first user here was actually requesting a very small amount of memory for what they were doing, but they were still only using a fraction of it in all of those jobs. But in this case, it's possible that this is something that we would dig down further into to see if the memory requests for the jobs could be reduced. And then after that, you get into the file system stuff. Now, the file system stuff doesn't impact scheduling at all. Storage is not used as a trackable resource in the billing or anything, but file system usage can have a very large impact on the performance of the job. So if you find that you're doing too much reading and writing and you're spending too much time in file operations, that can really affect the duration that you require. So monitoring how your file system operations are happening, you could reduce it. Now, file system operations can also impact other users that are on the same node and can impact the file system as a whole. So this is something else that we monitor closely, but not particularly for this discussion, which is more about job shape and doing the estimation. So pretty much a good time here. What I'm going to do is I'm just going to jump over to doing a demonstration of this. So I'm going to do the demonstration that I did in the 2-Minute Tuesday talk, where I'm on Narval, and I'm choosing Narval because it's one of the systems that has one of these usage portals that is sort of the state of the art where it's being pioneered right now. So I'm just going to submit an interactive job, and I'm just submitting it to my default account. Interactive jobs tend to have a very high priority and have resources that are sort of prioritized for this kind of use. And I'm just doing a simple job with a single task, and then just requesting 4 gigs of memory, which is sort of standard for a single core. Now, whenever this job gets allocated to resources, hopefully within a few moments. I had planned to start one before I got here, but I seem to have forgotten to do that. So what will happen is my terminal will then go to a compute node and have those resources allocated to it. So a single core with 4 gigs of memory, and then it will tell me which compute node it ended on. Once any user has a job that is active on a compute node, from another terminal, you can SSH into that compute node, and then from there, you can monitor what's actually happening on the node. And that's what I'll do on this terminal here. So I will SSH once I know the specific node identifier. I will SSH to it, and then I'll run top and I'll start to monitor the things. Now, hopefully this happens shortly. And then what I'll do from there is I will go here. So this is now the user summary. If I go to the Narval portal and I go to my user summary, it's possible that my internet is getting throttled. Of course, this is what will happen during a live demonstration. And then we'll take a look at what's happening. Okay, so this is starting to populate. The first thing that happens whenever I ask for my own user summary is we also get the file system quotas. Now, this is a very tricky thing. It's not related to the scheduling, which is the focus of this presentation, but you get to actually see where your own personal storage in home and Scratch is relative to the quotas you have, but also the project file system relative, and for each of the projects that you belong to, how you are doing relative to your quota. And then down below, what we have is a listing of all of the jobs that belong to the user that is signed into this portal. So here's the job that I just submitted. You can see the job ID here, ends in 122. It's pending. So importantly, this portal is live with the state of the cluster at the time. So you can even go here to check on your jobs that are pending. Down here are some of the jobs that I was just testing out 3 hours ago. So it failed. And the reason that it failed, I don't know, look at it. But if I click on this job, it will bring me to the properties of that job, which will happen slowly now because it's a live demo. So this is now the properties of that specific job that I submitted. So what it ends up giving is an overview. So Simone has worked in all kinds of alerts and interpretations of the job, and it will give warnings. For example, this one used less than half the CPU compute cycles that were allocated. And what that job is it's an interactive job that's requesting a single core and then a certain amount of memory. The interactive job basically puts the terminal on that compute node with those resources. And then I loaded MATLAB, I started building arrays, but I wasn't doing any processing on it. So this has flagged that. It said, you should check that job, because if this was an actual compute job and it wasn't doing anything most of the time, that's a problem, because you're going to end up bloating your resource request relative to what's actually needed. Yeah, and then so the other thing is I started MATLAB, which is notorious for starting a whole bunch of threads that are unnecessary, and batching things out. So then you get the actual time series of all of these things. This is the CPUs consumed. So we can see that it's actually, there's very little happening and it gets flagged in red. And then this was this thing that I was actually testing, although I haven't been able to demonstrate it in an interactive job, a new one now. This is what happened whenever I ran it previously, which shows the resources that were allocated to the job, which is in this case 4 gigs. Whenever I first started using it, I basically I loaded the MATLAB module and I started MATLAB, which initially jumps to almost 1.5 gigs. And then I started assigning different sized arrays inside of the MATLAB environment. And that would trigger basically these. This is the max used, and then these different these different views of what memory is. So typically, whenever I do the demonstration using top, we're actually watching the RSS memory amount. The RSS is what the scheduler uses to determine the amount of memory inside of a job. When the RSS exceeds the allocated, that's when a job is terminated. And I believe in this case, that's what happened, that the RSS, I assigned 2 different sized arrays. And then on the third one, I doubled it, which went above the allocated, which terminates the job prematurely. And then that's it. Yeah, and here's one of those, the MATLAB example where it starts a whole bunch of threads, but it really only uses a subset of them. And then there's a bunch of other information you can monitor about how the process in this job is actually using the hardware that it's been allocated to on a bunch of different levels that are beyond the scheduling itself. Okay, so the interactive job didn't start. I don't think I need to do that demo because I ran one of these earlier, and this is basically the output that we would get from it. So you know how to find it now. And in that job, what I would have done is just set different sized arrays and clear memory and then do things. And then you can actually look at the time series of the memory. And then whenever you submit the job, you have to make sure that you're allowing for the maximum required memory in the process, because anything that goes above what was requested gets killed. So I think with that, I can end it, and then I'd love to stick around and discuss some of these things if anybody has any questions.